So these are the spring 2019 exam 4 review slides. Some of that. So we're going to be talking about for chapter 5, or excuse me, chapter 15, and then the 17 and 18 condensed condensed chapters. Stuff like that. So these are going to be the free answer parts. Stuff like that. So you're going to have an electrophilic aromatic substitution. So it's you're going to be either adding the bromine or the chlorine. It doesn't matter. They work the exact same way. Now you are going to make sure, you do have to make sure that you deal with any formal charges, and I want to see the resonance structures. I'll have those in the instructions so you don't forget. Okay, so going from here to here. All right, so I'm going to put these lone pairs in. Okay, so these all work the same way, right? So one of the halides, right, the lone pairs are going to go towards your iron catalyst, and in doing so, it's going to rip off these electrons. So you're going to end up with Cl plus, and then Cl. This right here. This complex, which has a negative charge. You got yourself a positively charged thing here, right? So so in this case, the chlorine's going to want to go here. So you're going to take this bond. I'm going to draw on these hydrogens, and go there. Okay, and so so hydrogen chlorine. Right, and since this carbon only has three bonds, it's going to have the positive charge on it. So this is where the resonance structures come into play. Right, so this can slide down here. To do this. And then the chlorine hydrogen will be here and here. So about that. So you can also you can also move this double bond up here to make this resonance structure here and then there. But you can also do from this one, you can also have these lone pairs come in here. And this is the important one, because this is what determines that it's an orthopair director. And so you also need to put in this resonance structure here, where the thing with the lone pairs is going to go help out. In this case, it's the oxygen. And so it's going to look like this. Okay, so these are all the different resonance structures that are available. Okay, now what's then going to happen at some point, right? So this negative charge is then going to come down, grab the hydrogen off the carbon where you've added the chlorine, right? Because you go from one, right? We're going to go from a hydrogen to a chlorine, right? So we got to rip this away. These electrons here are going to come down and then reestablish the benzene here. Like that, plus HCl. Okay, so you're going to get one of those. That's the only mechanism I'm going to ask you about. Okay, so you are going to do. There's going to be some predicted product questions, some of that. So it's kind of getting broken up by reaction class, stuff like that. But there's only going to be 5 total. Stuff like that. So for here, you're going to need to know this chart generally, right? So what's an orthopair director, right? So it's going to be things that have either alkyl groups or things with lone pairs directly next to the benzene ring. Stuff like that. So that's going to be these are going to be the orthopair directors. Okay, the meta directors are things like C double bond O right next to the ring, C triple bond N, this is N double bond O, S double bond O, things like that. Those are going to be meta directors. Now these are all deactivating, so they actually slow down the reaction. These orthopair directors are these are deactivating, these are activating, so they make it go faster. These, even though they're ortho-pair directors, are actually deactivating because they're so electronegative. But you don't necessarily need to know the relative rate, stuff like that, except for the fact that everything's faster than an alkyl group, stuff like that. But but you don't necessarily need to know that this an ether is going to go faster than or slower than an OH. That's not a big deal. So for here, right? So you've got the right. So this is an alkyl group, right? So it's going to be orthopara. So this here puts the chlorine on. So you're going to need to have both the ortho and the pair product. I'll be sure to have that on the directions. Okay. Now for here, right, it's the same reaction we're putting chlorine on, but our director here has a C double bond O right onto it, and so therefore it's going to be a meta director. So that's going to be 2 away, so it's going to go here. Now it doesn't matter which of these 2 you put it on. It's going to be because it's the same molecules, just flipped. So in this case, the chlorine's going to go, say, here. Okay. So you're going to also have some of these. Something like that. I think there's 5 of these, where I give you a list of reagents, and you need to be able to match up how you go from, say, a benzene. You put a chlorine on a benzene, right? We just dealt with that. That would be this one here. With that, so if you want to put a bromine next to on a carbon adjacent to a benzene, right? So that's going to be the NBS. Here to put a sulfinic acid. So for that's going to be this guy here. So this is going to be I, and then for here to put on a fluorine, that is the F theta right there. So you just got to match these with these. So you're going to get one of these where it's the design of synthesis. Okay, so with that, so you're going to start with benzene, and then you need to figure out the reagents in order to be able to go here. And so you're going to need to know not only the how the reactions put things on, but also the order in which it puts it on. So you could do either one of 2 things, right? So you can put, say, so you could put the nitro group on first, okay, and then put the chlorine on, right? But this one right here, right, this is a meta director, right, because it's an N double bond O. So that's going to want to put the chlorine there. So that's not good. Okay. The other way that you could do it, right, is to put the chlorine on first. Right? Now this, because it's got the lone pairs, now this is an ortho-pair director, and you can assume, so it's gonna put the nitro group the next step, right? It's either gonna put it here, here, or here, and you can assume that it magically goes to which of the ones you need it to, or you could separate them. And so this is the order in which you're gonna have to put them on. You're gonna have to put the chlorine on first, and then put the nitro group. Okay, so how do we put a chlorine on? Well, it's the chloride and FeCl3. How do we put the nitro group on? Well, that's nitric acid and with sulfuric acid. Okay, so you're going to need to know not only the reactions, but how they work as far as orthopara. If for whatever reason you have 2 orthopara directors, but the product you need is in the meta position, what you need to do is go a slight detour where you're going to have to make one of those directing one of the groups a temporary meta director, and then so say, you know, the C double bond O, have it put on that way, and then remove it with, say, hydrogenation. Okay? So you'll also need to know need to know this list, right? That the order in which it goes, right? Because you can take an acid chloride, right, and go down, or you could go across, I guess, stuff like that. But you can't go back up the list, right? So an anhydride can make a thioester, an ester, or an amide, but you can't go up to make acid chloride. You can't go from ester to thioester, but you can go the other way, thioester to ester. Stuff like that. So you need to know this relative, make sure that the reaction goes forward. Okay. So for this one here, again, this is the type of critical product that we will see, right? So with that, here's your C double bond O, right? So here's the thing with the lone pair. So that's going to be your nucleophile. I don't need to know. I don't need to see this, but I usually draw it out just so we don't, just to keep things straight. So this is going to attack there. It's going to kick up to the oxygen, collapse back down, and then push away this group. So we're going to cut that away. And so what you're going to end up making is, and usually when this goes away, it'll grab a snag of hydrogen as it leaves, and so you'll get like that. Maybe I can put it here, right? And then this is the O, and then, right? Because all we've done is snip that bond. Okay, so all of that falls away. Okay, so this is your final product. So right, and then we're going from So we're going from thioester, right, to ester. Just double check, right? That's fine. We're going, right? We're going downhill from there to there. Now for this one here, right here's our C double bond O to attack, right? Because here's our acid chloride. Okay, so this is the negative charge that's going to attack. So this is going to go there, right? Up, down, kick away, right? So we're going to get this, and then right, plus Cl minus, right? So those electrons just ended up going onto the chlorine. That's that fourth set of lone pairs. Okay, and then this connects to this carbon here, right, to make this new bond. So this lone pair here became this new bond here, and everything comes with it. Okay, so there will be a design of synthesis starting from malonate. Okay, so the first thing you're going to want to do with this is figure out where this is in relation to this molecule here. Okay, and so this was originally, say, this was the ester here. This CH2, right, is actually, or this carbon here is actually this carbon here. Okay, and then it has hanging off of it the other ester that is going to go away. Okay, when we go through the final step, is always a base and then acid step that's going to decarboxylate. It's going to kick that whole thing away. Okay, so what we're going to need is this a 1 carbon piece here, okay, and then a 2 carbon piece here. This piece here is coming from the malonate. Okay, it's coming from right there. So we need a 1 carbon piece and a 2 carbon piece. It doesn't, in this case, it doesn't matter which one you put on first, right? So, but the process is always going to be the same. So the first thing you're going to want to do, right? I usually draw on the hydrogens to make it a little easier, right? So you're going to put in some hydroxide. That's going to grab this, put those electrons up here. So you're gonna make the carbocation, or excuse me, the carbanion. And then say we're going to put on this methyl group here. So, right, it's a 1 carbon piece where that bond is connected. It's going to be, you're going to need a bromine. So in this case, it's just going to be a 1 carbon piece with a leaving group, right? And then this is going to come down, simple SN2 chemistry, and so you're going to end up with so you have a methyl. So to put this 2 carbon piece on here, right? So that we go through this cycle again, where we add in hydroxide, right? That's going to come in, right? That's going to come in, grab that hydrogen, put those electrons back up there. And so you're going to get this, right? Like that. And now you need this 2-carbon piece here, so you're just going to dump in this case, ethyl bromide, like that. Right? This is going to do a simple SN2 attack. Right? So it's SN2, right? Just like we did here. It's an SN2 attack. And so what we're going to make is then we're almost there. Right? So we've got our ethyl group and our ethyl. Like that. Now, we need to get rid of one of those, and in the process, this is going to get turned into an OH. And that process, that decarboxylation process, is you have to throw in some sodium hydroxide first, and then put in some acid. And that will lop this part off, right? And then turn this O-ethyl into an OH. So like that. So this is the synthetic process. You don't need to draw in the mechanism. I'm just more interested in the synthesis, but I think drawing out the mechanism helps you keep this straight. I would also highly recommend either putting dots or putting the drawing it out like CH2CH3 as a condensed structure, just again to make sure that you're keeping all your carbons straight, stuff like that. So that's what I do, and it helps to visualize it. Okay, so the rest of this is just going to be reactions to know, right? So these are going to be so the alkylation, right? So if you're adding a carbon onto the benzene, you're going to need to use aluminum chloride. You have to be careful with it if it's just an alkylation where there's no C double bond O, because you can get rearrangement. So be careful with this. When you're doing the acid chloride here, you're never going to get rearrangement. Okay, so it's going to go here to here, no problem. Now to put the halides on, we know about these, right? So chlorine and iron chloride, or bromine and iron bromide. To put the fluorine on there, it won't work with the fluoride version, so you use an activating molecule called F-theta, and that will actually release the F plus, so that you can do this reaction. This one right here is also kind of a crazy. You just need to kind of know these. Stuff like that. These we're going to need to know the mechanism for the other question, but these you just need to know. Okay. So for here, to add a nitro group onto benzene, it's nitric acid plus sulfuric acid. To add the sulfinic acid, it's SO3 plus H2SO4. I've also seen it where it's just concentrated sulfuric, so fuming sulfuric or whatever it's called. So some of the other reactions to know, so KMNO4, that turns, if you have a CH bond here, right next to the ring, it turns that into a carboxylic acid and lops off the rest of the chain, no matter how big it is. And you'll be left with a carboxylic acid, right? So it's going to be left with that. Okay. Similarly with this one, so if it's a quaternary carbon right next to it, right, there's no CH bonds, so it's going to be unaffected. For here, that the MBS, right, again, it's one of those where if you have a CH bond next to a benzene ring, right, we can swap out one of the hydrogens for a bromine. If it's a quaternary carbon, so let's say methyl, 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 there's no hydrogens here, so that group's not going to get a bromine. Okay. Now with hydrogenation, stuff like that, so all this is saying is the benzene is going to be resistant. So under sort of normal conditions, it'll only reduce a regular alkene to an alkane. You have to pump it up to like 100 atmospheres of pressure in order to be able to reduce the benzene down to single bonds. Now, one of the quirks is that if you have a carbonyl here, so C double bonded directly adjacent to the ring, or to the benzene ring, under regular conditions, you can actually get turn this into a CH2. Okay, the C double bond O to there. Okay. More reactions. This is similar to what we were doing with the hydrogenation. You're turning this C double bond O into a CH2 here and here. This is done under basic conditions. This is done under acidic conditions. But this one does not have the need to be right next to the benzene, right? So there's no benzene here, but it still works. Something like that. So it just gives some options. So these are just the reactions where you've got, say, your nucleophile. This comes in, up, down, kick away, right? And then you have to know that the chart. This is one that's a little bit quirky that people don't always see for making the anhydride. The only way you can make it is an acid chloride because that's the only one above it. I guess you can make it from another anhydride. But again, it's going to be the same mechanism, up, down, kick away. But this whole group, right, is this whole group. It's no different than what we were doing here. Something like that. It just looks a little. Students sometimes have some issues seeing it, but it's no different. We're taking this lone pair, we're making a bond, we're swapping out the chloride for that bond there. It's no different than taking this lone pair and making a bond here after kicking that away. Okay. Now this one here, this is the thionyl chloride, SOCl2. Okay, so I'm going to actually list it as SOCl2. I was looking back at the old tests and the ACS final. You're going to need to know that this is the thionyl chloride. Its sole purpose in life is to take an OH and turn it into a Cl. Even if it's on a carboxylic acid, it turns an OH into Cl. You can also do that with an alcohol as well. So, okay. So for here, the LDA. Some of that you need to know that's the base. Again, I look back to the ACS final. That's what they were using. So I'd like to make sure that you've seen that. So this is just going to be a strong base, okay, and it's going to rip off the most acidic hydrogens on here is going to be one next to the C double bond O, something like that. So that's going to take this, move those electrons up here, and then that can do an SN2 reaction. Kick this away, and so that is the CH3 here. You can either do that with an alkyl bromide. You can also do this with, it's the same mechanism for here. If you had a molecular halide, right? So let's say you had BRBR, right? So in that case, you would attack, kick away. So, and to make this. So, okay. Good luck.